Right, this is the video on current. So just to start off, just to review a little bit, just the law of conservation of charge. This is at the heart, like what drives the unit of electrostatics. So the law of conservation of electric charge. Charge can neither be created nor destroyed. Charge can only be transferred from place to place, and the total amount of charge in the universe is fixed. Now, the fundamental rule, what really drives this, is like charges repel and unlike charges attract. So that's at the heart of electrostatics, right? The movement of electrons, and the reason why electrons move is because they're held to the atom uh, by the electromagnetic force, and the protons are held in place by the much stronger force. So when we're talking about transferring of charge, we're talking about the transferring of electrons. So now we're going to start to measure the force, the electromagnetic force, and we're going to talk about Coulomb's law. So this is a simulation that you can do. Is what you're doing is you have two different charges, right? So one's going to be -4. This first one is just about, well, what happens when you have opposites? What happens when you have the similar charge? And what happens when you have one neutral object? So remember, neutral is not a charge. So the first one is two negative charges. Well, you have two negative charges, they're going to repel. Now the next one, well, you have a -4 and a +4, so you have opposites, and they're going to attract. Now the last one is Q2 is 0, a neutral object, and that's going to be that there's no force, right? Because it's a neutral object. Now, yes, we did learn with polarization, what you can do is you can move part of that charge, but if you have something purely where none of the charge can be moved, just a neutral object, there is no electromagnetic force there. All right, so the next part was changing the charge, right? So one of the charges was at -4 microcoulombs, and then the other one started at 0 and was increased by 2 all the way up to 10, and then the force was recorded. And then the next one was increasing the distance. So the simulation only allowed 1.5 as the lowest, and then it went 2, 3, 4, 5, and the last one is 10. So you can't really see, my head cuts that off, but that's not the most important part. The most important is looking at the graphs here. So if we look at the charge versus force graph, I mean, or both of them, sorry, you look at the charge versus force and distance versus force, you can see that there's not much similar there. I mean, they're both on the positive x-axis, or above the positive x-axis, which is about what's really the only thing that's the same. You can see here the one up top is a linear going upward, the one going down is like a curved. So the relationship, if we look at the charge versus force graph, it's going to be a linear graph. It looks like a linear graph. It's a y equals x, and yeah, there's going to be like a little coefficient there, but that's the relationship. Then if we look at the next one, the distance versus force graph, you can see that it's an inverse squared relationship. So y equals 1 over x squared. So the last one says, if you wanted to maximize the force between the charged objects, would it be more efficient to increase the charge or decrease the distance between the objects? Explain your answer. And then I said, well, which variable, when manipulated, affects the force between the objects more? So what you should have gotten out of this one is that, like, if we use this as an example, let's just say we want the force to get as close to infinity as possible, right? Well, if we look at that top one, the charge versus force graph, it would take a long time for that graph to get to infinite. Like, yeah, I mean, it would take an infinite amount, but it would have to go up linear all the way. But you can see here in the distance versus the force, well, if I decrease it, notice it's going to keep continually going up. And just before it gets to 0, yeah, it will be infinite, like at a 0 distance. So just decreasing the distance, just that last part down to 0, will get that force to infinite really quick. So that brings us to this question: how does distance affect the intensity in the inverse square law? So that brought us to the inverse square law. And you can see here the intensity of certain phenomena is proportional to 1 over the radius, or that distance squared. So certain laws follow this. We have light, sound to an extent, just because that is affected by the medium which it's in. Spray paint, so this is a good visualization. Once again, it doesn't follow it exactly, because gravity would pull down spray paint. But you can just think about, like, if you spray paint something, it's going to be really thick if it's really close up, and it might drip, and then you say, whoa, I have to take a step back and spray paint just so I can get it thinner. It does follow like that inverse square law because it's covering an area. Gravity is affected by the inverse square law and the electromagnetic force. And just as a joke, I put butter because there is a video that you can watch where it's like somebody showing how butter, if you shot butter from a butter gun, how much toast it could do. Now, how much toast it could cover. Now, what I want you to notice is the variable r, or that distance, cannot be 0 because the intensity would be infinite, right? So just before, you would take an infinite amount, right? That's why, yeah. So it definitely gets to infinite as those distances get closer. Now, what I also want you to know is that the distance can never be large enough to make the intensity 0. So neither the intensity or that distance could be 0, right? It gets close. This is why we say the gravity and electromagnetic force have infinite range, because there's no distance that you could separate objects or charges where those would reach 0, right? So this was that demo. This is why you can never really touch anything, and it's because of the atoms, the electrons on the outside. Just before the electrons like touch, the force is infinite, repelling them away. So that's just sort of the sensation that we feel as touch. So now let's answer this question: how are astronomers able to measure the distance to stars using the inverse square law? So that's the same thing. Light follows that intensity. The inverse square law, the intensity of it. So if we know the like absolute brightness of a star, well, based on how bright it is here on Earth, we can measure that distance, right? And we learned about Cepheid variables. Those are certain stars that like sort of pulse at a certain rate proportionate to how bright they are, and this is how we were first able to determine the distances between galaxies and like give us that cosmic measuring stick. So now let's answer this question: what is Coulomb's law? So the electromagnetic force can be calculated with an equation called Coulomb's law. Now notice it follows the inverse square law, and Q1 and Q2 in that are going to be the charges. D or R, so it can be written both ways, D for distance, R for radius, is the distance between charges. K is Coulomb's force constant. So that's the equation. That's how we calculate that. So now let's sort of switch gears, and this is what let's talk about how the flowing of charges. So if we look at some bricks, right? So we know if we have 3 bricks at 1 meter and 1 brick at 2 meters, well, we know that the bricks on the left have more gravitational potential energy than the bricks on the right, right? So, you got 3 bricks, mass times gravity times height. We know that's going to be that. Now, the bricks on the left aren't going to fall towards the bricks on the right. That wouldn't make any sense. Even though, yeah, I mean, just because it has more energy than that single brick. What happens is all bricks or all objects fall from a position of higher gravitational potential energy to a position of lower potential energy. So that's what like similar to a siphon, right? So if you look at a siphon like flowing through, like 2 conditions must be met. That discharge reservoir must be at a lower position than the source reservoir, and it must have a tube filled with water to start the siphon. So water towers work very similar to siphons, right? Water flows from a high gravitational potential energy to lower gravitational potential energy. So that's what they do. They pump the water up so that way that water can flow down. So similar to gravitational potential energy, electric charge flows the same way. It will flow from high electric potential to low electric potential. Now, 2 conditions must be met for the flow of electric current. There must be a difference in electrical potential, and 2, well, there must be a conducting path. So electricity flow is similar to fluid flow. Voltage is the difference in electrical potential. That's the cause, similar to the water pressure in a siphon, and current is the flow rate of the electric charge. That's the effect. And it's similar to the flow through the tube of that siphon. So you can see off to the right, that's the siphon up top, and that's electric flow down on the bottom. All right, so if we look at some power lines, right, so some of the lines are hot, which means they have high voltages running through them. The transformer lowers the voltage to go from. Now, some of the wires and parts that are are lower voltages or ground. And we learned about what ground is. Anyway, so if anything were to connect them, that would give a path for energy to flow. So it's safe to it's safe going through that as long as it's at a high potential, but as long as nothing connects those two, right? Which brings us to another question. Well, why can birds sit on a power line without being shocked? Well, as long as you can be at a high potential, you can be at a high electric potential, that's perfectly fine. As long as you are not the path from high to low potential, you're gonna be fine. So that's what birds do. Yeah, they sit on the high power lines, they're at a high energy, but they're never connecting to another lower potential that would shock them. So now, what should you do if a power line falls across your car, right? So, let's just look. So, I must iterate that if you can safely stay in your vehicle, you should remain there until proper authorities arrive. But if someone must escape, like the car is on fire, they must be careful of electric potential. So we watched a video of somebody escaping. So we also watched this PSA on it about talking about how to safely get out of a vehicle. So let's look at why you get shocked if a power line is down. So touch potential, right, is what happens when you connect the higher potential of the car to the lower potential of the ground. You can see that picture up top. He's connecting the higher potential to the lower potential because he just grabbed the car and stepped down. You do not want to connect high to low potential. Now, step potential is when you take a big step and connect a higher potential ground to a lower potential ground. So here are some steps to take if you're in a car close to a down power line and you must escape. Like I said, if you can stay in the car, stay in the car. But if you must leave the car, jump as far from the car as possible with your feet together. This will take you to a high to a low potential, but you do not connect them. Then when you walk away, shuffle. So that way you're not connecting a high to a low potential across the ground. Which brings us to this question. How can someone increase their chances of surviving a lightning storm? Well, it's the same thing, right? So this is why you do not want to be the tallest or even the tall or the tallest object, even the or close to the tallest object when lightning strikes. Charge spreads outward along the ground. You may bridge two different lines of electric potential. So to survive a lightning strike, put feet together and crouch down. This will decrease the electric potential across your body. So interesting fact, males are 5 times more likely than females to be struck by lightning. Around 85% of lightning fatalities are men. This just has to do with because a lot of lightning fatalities happen while fishing or an open sports field. So that's why it's usually why those are predominantly male. Or it's not that it's not that women don't do these. It's just that most fishing is a predominantly male uh, hobby. And I always joke around and say, hey, maybe guys just don't have the common sense. When lightning comes in, the women are like, well, let's head inside. But that's just a little interesting fact about lightning. Most of it does occur in like open fields or fishing. So I always just say if you want to avoid being struck by lightning, don't be a male fishing in July. And you can see those. There are links that have graphs of when lightning strikes happen the most. But yeah, this is how you will. I mean, obviously, first thing you probably want to get to shelter, but if you can't, this is how you would survive like a lightning storm. So now let's answer this question. Does lightning ever strike the same place twice? Well, the answer is yes, because it strikes the tallest point a lot. In fact, you can watch videos of, skyscrapers want to be struck by lightning so they can disperse that energy downward safely and protect like the other buildings around them and all the electrical equipment inside. So let's answer this question though. Why are four-legged animals more vulnerable to lightning strikes than humans? So this brings us to cows and lightning. So where do cows spend most of their time? Well, cows spend most of their time in an open field, which is a bad place to be in a lightning storm. And also, if we answer this question, what other reason do cows have a large disadvantage when lightning strikes close to them? Think about how you should walk away from the car during a down power line. Well, cows' feet are farther apart, right? So we can keep our feet together because we're walking on two legs. They're far apart, and there's a larger difference in electric potential. So now let's talk about current. So current is the flow rate of electric charge. It is a measure of the number of charges that pass through a certain cross area of wire per second. So it is not a measure of how much, but rather how fast that charge is flowing through a given cross-sectional area. It's sort of like a speed, like miles per hour. It's like charge per second, basically. So in solid conductors, electrons are loosely held by atoms. Thus, they are the charges that are free to move in a conductor, right? So let's just take a look. So current is the flow rate of electric charge, number of charges through a given area of wire, unit of time. And we use the symbol I. You can see that equation off to the right. I equals the difference in charge divided by the time interval, right? And it's French for like the intensity. So the unit for electrical current is the ampere, or the amp. So 1 ampere represents a considerable amount of charge. It's the flow of over 1 billion electrons per second. So a large electric current corresponds to a large number of electrical charges flowing through a given cross-sectional area of wire. So to measure water flow rate, your local water company uses a water meter, which measures the number of gallons of water that you use in your home. Now, to measure electric current, an ammeter is used, and it's a similar concept. So now let's get to this, right? I call this Ben's mistake, right? Because we're talking about Benjamin Franklin and his mistake. So we constructed this circuit off to the right, and when the switch is open, does the current flow? Well, no, it's not, because remember, two conditions have to be met. There must be a difference in electrical potential, which is provided by the battery, and there must be a connection between the two different electrical potentials. And you can see in that, like, it's not. The switch is open. Now, when the switch is closed, then yes, those two conditions are met. The battery provides the electric potential, and that the closing of that gate completes that circuit. Then the last one is bringing the battery down to 0 with the circuit closed, or with the switch closed, and nothing flows because there's not a difference in electrical potential. That is the condition that was not met. So the last one says click on the box of conventional current. And you can see here that you can't really see on this one, but if you did the simulation, you'd see that the conventional current is going in the opposite direction of the flow of electrons. Now that brings us to this question. Ben Franklin thought current was the flow of fluid and thought the fluid would flow from positive to negative. This is what we describe as conventional current. Was Ben Franklin wrong about the flow of electric charge? If so, why do you think he made this mistake? Explain your answer. Well, he was wrong. He had to guess, basically. He had to guess. He just basically thought, okay, I think I've got these two charges, which he came up with those terms. And he said, well, there must be some fluid flowing back and forth to balance it out. He just kind of guessed. Goes from positive to negative, right? We can't see atoms. We can't see electrons, right? So he just basically had to guess. So let's answer this question. How was the discovery of electric charge indirectly responsible for American independence? So that takes a look at Ben Franklin, right? So up until Ben came along, electricity was a parlor trick. No one really understood it. Like, they would be, these shows of like where people would just get shocked, right? People knew that if you rubbed amber with fur, something would stick to that amber, right? In fact, the Latin word for amber is electrum, which is where the word electricity comes from. So Ben, with his kite and key, showed that lightning was electricity and not supernatural. He was the first to describe this phenomenon of electricity, just like Newton was the first to describe gravity. So Ben Franklin became a rock star overnight and was held in high regard by the King of France, whom he convinced to intervene in the American Revolution. So this is just some final thoughts. There is too much unknown in the universe to take a break from learning. Get out there and question everything.